My dear students, hello. Today we will discuss the basic building blocks of a computer. The topics that will be covered today are logic gates, Boolean algebra and combinational circuits. Why do we need logic gates? Logic gates are in fact the building block of digital electronics. They are formed by the combination of transistors to realize some digital operations. Every digital product like computers, mobiles, calculators or even digital watches contain logic gates. So, logic gates are used in almost everything digital that we use for daily purposes. So, let us begin with logic gates. A logic gate is an idealized or physical device implementing a Boolean function, that is, it performs a logical operation on one or more logical inputs and produces a single logical output. Logic gates are primarily implemented using diodes or transistors acting as electronic switches, but can also be constructed using electromagnetic relays. Boolean functions may be practically implemented by using electronic gates. The following points are important to understand. The first one is electronic gates require a power supply. Gate inputs are driven by voltages having two nominal values, for example 0 volt and 5 volt, representing logic 0 and logic 1 respectively. The output of a gate provides two nominal values of voltage, example 0 voltage and 5 volt, representing logic 0 and logic 1 respectively. In general, there is only one output to a logic gate. There is always a time delay between an input being applied and the output responding. Logic gates extensively use truth tables. Truth tables help us to understand the behavior of logic gates. They show how the input of a logic gate relate to its output. We will see these truth tables soon with the help of examples. Now, coming back to logic gates, we have many logic gates such as AND, OR, NOT, NAND, NOR, XOR and XNOR gates. The basic operations of these gates are described with the aid of truth tables. We will discuss these gates one by one. Let us start with AND gate. The AND gate is an electronic circuit that gives a high output, that is 1, only if all its inputs are high. A dot is used to show the AND operation, that is A dot B. Bear in mind that this dot is sometimes omitted, that is, we can simply write A B. Look at the diagram. This is the representation of AND gate along with its truth table. Here A and B are the inputs and AB is the output. We can also replace this output AB with A dot B as already discussed. In the truth table, when one of the input A or B is 0 or low, then the output AB is 0. We can easily notice that the output is 1 only when both the inputs A and B are 1, else it is 0. So, the output is high only when both the inputs A and B are high. Now, let us learn OR gate. The OR gate is an electronic circuit that gives a high output, that is 1 if one or more of its inputs are high. A plus is used to show the OR operation. Look at the diagram. This is the representation of OR gate along with its truth table. Here A and B are the inputs and A plus B is the output. In the truth table, we can easily notice that the output is 1 only when either of the inputs A or B is 1 or both the inputs A and B are 1. The output is 0 only when both A and B are 0. So, next is NOT gate. The NOT gate is an electronic circuit that produces an inverted version of the input at its output. It is also known as inverter. If the input variable is A, then the inverted output is known as NOT A. It is represented by A complement or A with a bar over the top. Look at the diagram. This is the representation of NOT gate along with its truth table. Here A is the only input and A bar is the output. In the truth table, we can easily notice that the output is 1 when the inputs A is 0 and is 0 when the input A is 1. So, basically NOT gate inverts or toggle the value of the input. Now, we will discuss about NAND gate. This is a NOT AND gate which is equal to an AND gate followed by a NOT gate. The output of a NAND gate is high if any of its input is low. Look at the diagram. This is the representation of NAND gate along with its truth table. Here the small circle represents inversion. A and B are the inputs and AB bar is the output. AB bar is nothing but the product of A and B followed by the complement of the result. In the truth table, we can easily notice that the output is 1 only when either of the inputs A or B is 0 or both are 0. Hope NAND gate is clear to you. Our next topic of discussion is NOR gate. This is a NOT OR gate which is equal to an OR gate followed by a NOT gate. The outputs of a NOR gate is low if any of its input is high. Look at the diagram. This is the representation of NOR gate along with its truth table. The symbol is an OR gate with a small circle on the output. The small circle represents inversion. Here A and B are the inputs and A plus B bar is the output. A plus B bar is nothing but the OR operation on A and B followed by the complement of the result. In the truth table, we can easily notice that the output is 1 only when both of the inputs A or B is 0, otherwise it is 0. So, next is XOR gate. The exclusive OR gate is a circuit which will give a high output if either but not both of its two inputs is high. Look at the diagram. This is the representation of XOR gate along with its truth table. An encircled plus sign is used to show the XOR operation. Here A and B are the inputs and A plus B with a circle is the output. In the truth table, we can easily notice that the output is 1 only when either of the inputs A or B is 1, else it is 0. Now, we will study XNOR gate. The exclusive NOR gate circuit does the opposite to the XOR gate. It will give a low output if either but not both of its two inputs are high. Look at the diagram. This is the representation of XNOR gate along with its truth table. The symbol is an XOR gate with a small circle on the output. The small circle represents inversion. Here A and B are the inputs and A plus B encircled along with a bar is the output. In the truth table, we can easily notice that the output is 0 only when one of the input A or B is 1, else it is 0. It is worth noting that NAND and NOR gates are called universal functions, since with either one the AND gate or OR gate or NOT gate can be generated. Now, we will learn about Boolean algebra. Boolean algebra has similar rules to other algebras, and these rules are used to manipulate the expression at hand. Look at the table. These are the basic rules of Boolean algebra. For one variable, a dot a gives us a. Here dot refers to the AND operation. Similarly, a plus a gives us a. Here plus is OR operation. Similarly, if we take one variable along with a value 0 or 1, then the result of AND operation on a and 0 is 0. For a and 1, it is a. Similarly, the OR operation on a and 0 gives us a, and of a and 1 gives us 1. Next is the De Morgan's theorem. It states that the complement of the OR operation of a and b taken as a whole is equal to the AND operation on complements of a and b. Similarly, for second case, the complement of the result obtained by doing AND operation on a and b is equal to the result obtained by applying OR operation on the complements of a and b. So, next is the associative property. It states that the result of AND operation on a and b when again ANDed with c gives the same result as we get when we apply the AND operation on b and c and then with a. Similarly, we can infer the result for the second case. Then comes commutative property. It is very similar to the associative property. It states that a when ANDed with b gives the same result as b ANDed with a. Similarly, a or b operation gives the same result as doing b or a. So, now coming to the last property called distributive property. It states that the result of OR operation done on b and c when ANDed with a is equal to the OR operation of two results obtained by ANDing a with b and a with c. Similarly, the second case says that the result of applying OR operation on a and the product of b and c is equal to the result obtained by applying the AND operation on the two results obtained by adding a with b and a with c. Note, OR operation is represented by the plus symbol and has the lowest precedence. NOT operator is represented by the complement symbol and has the highest precedence. AND operator is represented by a dot symbol and is in the middle of the precedence list. Hope Boolean algebra is clear to you. Now comes one of the most important topic called combinational circuits. We have actually two types of logic circuits, sequential and combinational logic circuits. Sequential logic circuits are those whose outputs are dependent on both their present inputs and their previous output state, giving them some form of memory. The outputs of combinational logic circuits are only determined by the logical function of their current input state, logic 0 or logic 1 at any given instant of time. The result is that combinational logic circuits have no feedback, and any changes to the signal being applied to the inputs will immediately have an effect at the output. In other words, in a combinational logic circuit, the output is dependent at all times on the combination of its input, and if one of its input condition changes state, so does the output, as combinational circuits have no memory. Look at the diagram of combinational circuit. A combinational circuit has multiple inputs and multiple outputs. Combinational logic circuits are made up of basic logic NAND gate, NOR gate or NOT gates that are combined or connected together to produce more complicated switching circuits. These logic gates are the building blocks of combinational logic circuits. An example of a combinational circuit is a decoder, which converts the binary code data present at its input into a number of different output lines, one at a time, producing an equivalent decimal code at its output. Combinational logic circuits can be very simple or very complicated, and any combinational circuit can be implemented with only NAND and NOR gates, as these are classed as universal gates. As combinational logic circuits are made up from individual logic gates only, they can also be considered as decision making circuits, and combinational logic is about combining logic gates together to process two or more signals in order to produce at least one output signal according to the logical function of each logic gate. Common combinational circuits made up from individual logic gates that carry out a desired application includes multiplexers, demultiplexers, encoders, decoders, full and half adders, full and half subtractors. Now we are going to discuss various combinational circuits. First one is half adder. Digital computers perform a variety of information processing tasks. Among the basic functions encountered are arithmetic functions. The most basic arithmetic operation is the addition of two binary digits. We have basically four possible elementary operations of addition, and they are, as you can see in the diagram, 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 1 0. The first three operations give us a single digit after the addition of two digits, whereas the fourth operation gives us two digits at the output. The higher order digit in this case is called carry. Half adder is a combinational logic circuit with the two input and two output. The half adder circuit is designed and add two single bit binary numbers A and B. It is the basic building block for addition of two single bit numbers. This circuit has two outputs, carry and sum. This is the block diagram of half adder along with truth table and logic circuit. Here A and B are the inputs and outputs are sum S and carry C. In the truth table as well as logic circuit, the input is represented by X and Y. Here we can easily notice from the truth table that carry C is 1 only when both the inputs X and Y are 1. Also we can see that the logic circuit can be developed using AND gates and OR gates. Now we will study about full adder. As we have already studied half adder, and we know that half adder can add only two single digit numbers, but what about the carry bit? So this is a limitation with the half adder. Full adder is developed to overcome the drawback of half adder circuit. It can add two 1 bit numbers A and B and a carry C. Thus in a full adder we have three inputs and two outputs. This is the block diagram of full adder along with truth table and logic circuit. Here we can easily see that there are three input digits as compared to 2 in the case of half adder. Here we can see that we have three inputs A, B and C in and two outputs S and CO. The inputs A, B and C are represented by X, Y and Z in the truth table as logic circuit. By looking at the truth table, we can see that using full adder we can add the two inputs as well as the carry from the previous stage and will give the output as C and S. Further, we can conclude that we can develop full adder circuit by using AND gates and OR gates. Now, let us study half subtractor, which is another combinational circuit. Half subtractor is a combination circuit with two inputs x and y and the two outputs b and d. It produces the difference between the two binary bits at the input and also produces an output borrow to indicate if a 1 has been borrowed. In the subtraction x minus y, x is called as minuend bit and y is called as subtrahend bit. B is the borrow and D is the difference. Let us see the truth table and we can easily notice that the only case where we need to borrow 1 is when we subtract 1 from 0. It is interesting to note that the logic for D is exactly the same as for S in the half adder. Now, the next circuit we are going to study is full subtractor. The full subtractor is a combinational circuit with three inputs x, y and z and the two outputs b and d. X is the minuend, y is the subtrahend, z is the borrow produced by the previous stage, d is the difference output and b is the borrow output. It overcomes the limitation of a half subtractor, which is that the half subtractor does not consider the borrow from the previous state. As you can see in the truth table here, first y is subtracted from x, that is we perform x minus y and then subtract z from the result obtained from the expression x minus y. The generalized expressions for both difference and borrow are also shown. Our next topic of discussion is a very important topic called multiplexers. Multiplexer, which is also called mux, is a special type of combinational circuit. Let us see the block diagram of a generalized multiplexer. There are n data inputs, 1 output and m select inputs. M is equal to log n base 2. It is a digital circuit which selects one of the n data inputs and route the data from it to the output. The selection of one of the n inputs is done by the select inputs. Depending on the digital code applied at the selected inputs, one output of n data sources is selected and transmitted to the single output y. E is called the strobe or enable input, which is useful for the cascading. It is generally an active high terminal, that means it will perform the required operation when it is high. Multiplexers come in multiple variations. We have 2:1 multiplexer, 4:1 multiplexer, we have 16:1 multiplexer, 32:1 multiplexer. In a 2:1 multiplexer, we have two inputs, one select input and one output. This is the block diagram of 2:1 multiplexer along with its truth table. As in the truth table, when E is equal to 0, then don't care condition arises, because when E is equal to 0, the circuit will not operate and hence no input will be selected. As value of E becomes 1, the circuit will be activated and depending on the select input, an input will be selected and sent to the output. Similarly, in 4:1 multiplexer, there are 4 inputs and 1 output. Similarly, we can calculate the same for other multiplexers. Hope multiplexers are clear to you. So, now we will study another combinational circuit called demultiplexers. A demultiplexer, also called demux, performs the reverse operation of a multiplexer, that is, it receives one input and distributes it over several outputs. It has only one input, n outputs, m select input, where m is equal to log n. At a time, only one output line is selected by the select lines and the input is transmitted to the selected output line. A demultiplexer is equivalent to a single pole multiple way switch. Demultiplexers come in multiple variations, like we have 1:2 demultiplexer, 1:4 demultiplexer, 1:16 demultiplexer and similarly we have 1:32 demultiplexer. In a 1:2 demultiplexer, as we can see in the figure, we have only one input, one select input and two outputs. When E is equal to 1, that is when strobe is enabled, then depending on the select input, the input value is sent to the selected output. Similarly, in 1:4 demultiplexer, we have one input, two select inputs and four outputs. Selection of the output depends on the two select inputs. Similar is the process for other demultiplexers. Now, let us discuss another combinational circuit called decoder. Discrete quantities of information are represented in digital systems with binary codes. A binary code of n bits is capable of representing up to 2 power n distinct elements of the coded information. A decoder is a combinational circuit that converts binary information from n input lines to a maximum of 2 power n unique output lines. If the n bit decoded information has unused or do not care combinations, the decoder output will have fewer than 2 power n outputs. The decoder presented here, as you can see in the diagram, is called n to m line decoder. Its purpose is to generate the 2 power n minterms of n input variables. The name decoder is also used in conjunction with some code converters such as BCD to 7 segment decoders, Nixie tube decoders and relay actuator. As we can see in the figure, we have a 3 to 8 decoder where we have 3 inputs and 8 outputs. The logic circuit has 3 inverters which provide the complements of the inputs, and each one of the 8 AND gates generates one of the minterms. A particular application of this decoder would be a binary to octal conversion. The input variables may represent a binary number and the outputs will then represent the 8 digits in the octal number system. However, a 3 to 8 line decoder can be used for decoding any 3-bit code to provide 8 outputs, one for each element of the code. Now, coming to the final topic for today, and that is encoder. Encoder is a combinational circuit which is designed to perform the inverse operation of the decoder. An encoder has 2 raised to power n number of input lines and n number of output lines. An encoder produces an n bit binary code corresponding to the digital input number. An example of an encoder is the octal to binary encoder, whose truth table shows that it has 8 inputs, one for each of the octal digits, and 3 outputs that generate the corresponding binary number. It is assumed that only one input has a value of 1 at any given time, otherwise circuit has no meaning. Other examples of encoders are priority encoders, decimal to BCD encoder, octal to binary encoder and hexadecimal to binary encoder. So, with this we complete our first lecture, and concluding this lecture we can say that logic gates forms the basis of combinational circuits which are frequently used in digital applications of our daily use. In the next lecture we will cover circuit simplification and memory hierarchy. Thank you.